So welcome again to the week 7 problem solving session for the course Environmental Chemistry. Of the TA for this course, my name is Asma Parveen. I am a PhD scholar in Civil Engineering Department at IIT Kanpur. I hope you all have gone through the lectures. So in week 7, the week 7 lectures was about alkalinity and acidity and its application. There was various numericals which were solved on based on these concepts. There was concept of mixing of two solution. What are the conservative parameters and what are the non-conservative parameters, and also there were numericals based on these. And in the last lecture, it was about anaerobic digesters and fermentation, and the numerical was also solved on the basis of that. So what we are going to do is that we will see the previous year previous year assignment questions, and we will try to solve that questions. So first let me zoom in this. So the first question is, a wastewater is simulated as an ideal solution containing this much of sodium bicarbonate and this much of ammonium chloride. The utility hopes to remove nitrogen from the solution by volatilizing ammonia gas. To prepare for that step, 148 milligrams per liter of lime will be added to raise the pH and convert to ammonia aqueous form. The pH before and after lime addition assume that no calcium carbonate precipitation or ammonia loss takes place during the lime addition, that is, all species remain in solution would be. So we have been given a wastewater and which contains sodium bicarbonate and ammonium chloride. These two are used to simulate the wastewater, and we have to volatilize the ammonia gas. And as we know that ammonium ion converts to ammonia aqueous at pH around 9.2. So the aim is to increase the pH around 9.2 or more than that by addition of base, that is lime, so that ammonium will be converted to ammonia aqueous, and that will be finally converted to the gas. So we have to find out the pH before and after the lime addition. So just wait a minute. So let's see what are the concentration of all the components present in the system. So we have NaHCO3s 10 raised to power minus 2.5 m. And again we have ammonium chloride, which is 10 raised to power minus 3 m. So the components will be sodium, and we can see from this that 1 mole of sodium bicarbonate will give 1 mole of sodium. So we have Na total equals to 10 raised to power minus 2.5 m. So let's see what are the other components present. And again we will have total CO3, that will be again equal to 10 raised to power minus 2.5 m, because sodium bicarbonate will dissociate in sodium and bicarbonate, and as soon as bicarbonate is formed, then it can, depending upon the pH, it can complex with H plus and form carbonic acid, or also it can further lose its hydrogen and can form carbonate, but the total concentration of the carbonate will be same, that will be 10 raised to minus 2.5 m. Next, we will have total ammonium, that will be equal to 10 raised to minus 3 m. Then again we will have total Cl, that will be equal to 10 raised to minus 3 m, and we have to see what will be the concentration of total H, because this NaHCO3, this can dissociate and form Na plus and HCO3 minus, and further HCO3 minus can dissociate to form H plus and carbonate. So total H plus, total H will be, sorry, just give me a minute. So total H will be 10 raised power. Can you please wait for a second? And total H will be equals to 10 raised power minus 2.5 m. So these are the components which we are going to add in the visual Mintake, and we will run the Mintake and we will see what is the pH. So we have total sodium as 10 raised to minus 2.5 m. Let me write it as TOTN. Total carbonate as 10 raised to minus 2.5 m. This is the total ammonium, total chloride and total H. So we have 5 components. We are going to add these components in the visual Mintake. So let me open the visual Mintake and see what is the pH before the addition of calcium hydroxide. So now I will share the screen with visual Mintake. So let's start. So this is the visual Mintake. So we are going to calculate the pH. So we will calculate the pH from mass balance. Ionic strength will be to be calculated. Now we will add all the component name. So first we were adding sodium Na. So Na was 10 raised power minus 2.5. So we can write 0 point, sorry, 0.00. So let me write 1 E minus 2.5. So we will add it to the list. Then again we will add. So let me see if it has been added. Yes, Na has been added. So next was total carbonate. So we will add the carbonate species. So carbonate is also 10 raised to minus 2.5. So we will add to the list. Next species was ammonium NH4 plus, and it was 10 raised to minus 3. So 10 raised to minus 3, add to list, and again we will having chloride. It was also 10 raised to minus 3. We will add to the list, and finally we were having H plus, total H. And total H was 10 raised to minus 2.5. So 10 raised to minus 2.5. We will add to list. There was nothing mentioned about opening or closing of system, so we will assume the system to be closed. So let's see what are the components which we have added. So these are the components which we have added. We have added H plus, we have added sodium, we have added carbonate, ammonium and chloride. And since, let's run this and see what is the pH. We will run the Mintake, and the pH is 8.107. Eight point 107 is the pH. Next, in the second part, what is it? It is being said that we are adding lime for the volatilization of the ammonia. So let's move to the second part. We will go back to the input menu. And now how much? So we are adding 48 milligrams per liter of the calcium hydroxide. So Ca, I'm sorry because I am writing it with cursor. Calcium hydroxide is 148 milligrams per liter. So we can also convert it into moles, or we can directly add into Mintake. Let's convert it into moles. Let's find out what is the molecular weight. So molecular weight will be 40 for calcium plus 2 moles of oxygen. So 2 into 16 plus 2. So let's see what is the overall molecular weight of calcium hydroxide. So 40 plus 2 into 16. So it is 74 grams per mole. So in terms of moles per liter, calcium hydroxide will be 148 upon 74, and 148 will be divided by 1000, so it will be 2 millimolars. Because 148 upon 74 into, sorry for my handwriting, 1000. So, and as from the equation we can see that 1 mole of calcium hydroxide will give 1 mole of calcium and 2 moles of hydroxide. So Ca, let's write what will be the Ca total. We can write total Ca as this also, that is equal to 2 millimolars. And we will see what is the total H plus, total hydroxide, hydronium ion. So initially In the system there was 10 raised to power minus 2.5 m. Okay, and now we have hydroxide is being added in the system, and as we know, if there is hydroxide in the system, it will take H plus and form H2O. So obviously the H plus concentration will decrease. So let's see how much it will decrease by addition of calcium hydroxide. So we have 2 moles of hydroxide by each mole of calcium hydroxide. So 2 into 2 into 10 raised to power minus 3. So this will give us the total H plus as minus 8.38 into 10 raised to power minus 4 m. So in our new system, we have added additionally calcium and H plus, and H total has changed. So we will go to the Mintake, and since we are trying for volatilization of the ammonia, so the system will be open to the atmosphere. So we will specify the partial pressure of carbon dioxide. So let's go. Sorry, we will not open the system because there is nothing mentioned about opening or closing of the system. So the system will remain closed, and we will find out the pH after addition of calcium hydroxide. So let's go back to Mintic. So let's see what are the species which we have already added. So these are the species added. Let's go back and add a additional component, that is calcium. And calcium is present as 2 into 10 raised to power minus 3. So let's change this. So we will add the calcium carbonate and its concentration. And also we are going to edit the concentration of H plus, because earlier it was 10 raised to power minus 2.5. Now it has changed to minus 8.38 into 10 raised to power minus 4. 8.38 into 10 raised to power minus 4. I don't know. Okay. So this is the new H plus concentration. We have already added sodium, carbonate, ammonium, chloride, and now we have added the calcium. We will go back and we will run the Mintec. And now we can see the final pH is 10.923. So let's note it down. So the pH is 10.923, I guess. And before that, earlier the pH was, I guess, 8.1 or something. So let's see what are the options which are given. So let's go to the previous slide. So earlier the pH was 8.1 and now we are getting the pH as 10.92. So first option is the correct option. So let's move to the next question. So these are the screenshots which I have added from the Visual Mintic for solving this question. So next question is, a raindrop formed in a cloud passes over a smokestack and absorbs this much of sulfuric acid. The droplet next passes over a cattle feedlot and comes to equilibrium with ammonia gas of partial pressure this much, while remaining in equilibrium with atmospheric CO2. The pH and total dissolved nitrogen of the solution is. So there is a raindrop in the atmosphere, and as we, and it and it's while passing over, it absorbs some H2SO4, and again it is in passes over a cattle feedlot and again absorbs ammonia gas, and it is so and since it is in atmosphere, it is in equilibrium with ammonia as well as the CO2 gas in the atmosphere. So we have to find out what is the pH and what is the total nitrogen concentration of the solution. So let's see. For this question, we are also going to use visual minting. So we have, let's see, what are the components here. So the raindrop absorbs 10 raised per minus 5 molar H2SO4. So total, and as we know, each mole of H2SO4 will give us 2 moles of H plus and 1 mole of sulfate ion. So total H will be 2 into 10 raised to the power minus 5 m. And total sulfate SO4 that is equals to 10 raised to the power minus 5 m. Now we have been given the partial pressure of ammonia gas, which is above the cattle feedlot. So the partial pressure there is 10 raised to the power minus 10.2 atm. So we have to find out the pH, and also it is in equilibrium with atmospheric CO2. Its partial pressure is not given, so we will use the partial pressure already present in the visual Mintek, which is the atmospheric CO2 pressure. So let's add the components. Let's go back to Mintek. So we have solved the previous question. First we will reset it. Now we have to add total H. So total H is 2 into E to the power of minus 5. Okay, we will add it to the list. Next we have sulfate SO4 minus 2, it is 10 raised per minus 5. So 1 E to the power minus 5 we will add to the list. Next we have two other gases which are present, and it is in equilibrium with the droplet. So we will go to the gases section. It was given in the question that it is in equilibrium with the atmospheric CO2. So we will add this one. So I have added it. And also it was in equilibrium with the ammonia gas with the given partial pressure. So we can choose the gases from this database. So here we have to select ammonia. Let's see where it is. NN. So here it is the ammonia gas. So as soon as we added the ammonia gas, log K and delta H has it has automatically appeared. Now we have to add the partial pressure. And it was given that the partial pressure is 10 raised to power minus 10.2. So 1 E minus 10.2. We will add it to the list. Let us see if we have added both or not. So in the fixed species we have carbon dioxide and ammonia. So let's go back to the main menu and we have to calculate the pH from mass balance. So let's run the Mintech. So the pH which we are getting is 5 point something. It is 5.694. And we can find the concentration of nitrogen because we have to find out how much moles of nitrogen. So this is the NH4 plus will give us the concentration of nitrogen. So we have to find the pH and the total dissolved nitrogen of the solution. So we know that total dissolved nitrogen will be the NH4 plus. Let's go to the equilibrium mass distribution. So from the component, these are the component distribution. So the total dissolved nitrogen will be this much. This is the total dissolved nitrogen, that is 2.0837 into 10 raised power minus 5. So this is the total dissolved concentration of the nitrogen. Let's go back. So basically what we have done, we have added all the components, we have added the partial pressure which was given, and we have calculated the pH. And next question was we have to find out the total dissolved concentration of the nitrogen. So we can see that there are two forms of nitrogen which are dissolved, that is the NH4 plus, NH3 aqueous, and also there is one more form, that is NH4SO4 2 minus. So we can add these or directly we can go to the equilibrated mass distribution. We will get the mass distribution of all the components which are in the dissolved form, and these columns we will see in the later sections, in the later weeks. So here we can see that the component ammonia concentration is this much. So this is the overall concentration of dissolved ammonia. So we'll go to the back menu, then we will go directly to our slides. So what we have calculated, let us write it down. So the pH was 5.694 and the overall concentration of dissolved nitrogen, it was 2.084 into 10 raised power minus 5 m. So this is the final pH and this is the final dissolved concentration of the nitrogen. Also, I would like to mention it out that we have taken the component NH4 plus and we are reporting it as the total dissolved nitrogen because we can see that in NH4 plus it has 1 mole of nitrogen per mole of ammonium. So the concentration of ammonium in moles will be equal to the concentration of the nitrogen. So the concentration of nitrogen will be this. So let's see which is the correct option. A is the correct option, that is pH is 5.69. And concentration of total dissolved nitrogen is 2.08 into 10 to the power minus 5. So let's save it. Let's move to the next question. So like previous question, I have added all the components. You will get this as the PDF. I will upload it in the drive. You will get the link for this. So let's move to the next question. I think this question is about mixing of two solution. two water at 25 degrees centigrade are in equilibrium with air, one at pH 9.5 and one at pH 6.5. So we have been given two waters which are in equilibrium with air. The system is open. The pH of each water is given. These water are mixed in proportion of 1:5. Okay. Assuming that carbonate species dominate the acid-base behavior of both the solution and that no gas transfer occurs when they are mixed, that while they are mixed the system is closed. Earlier the system is, we will find the pH is given and the system are open, both the system are open, and while mixing and after mixing these systems are closed. So we have to find out the alkalinity and pH of the mixture. So as we know that alkalinity is the conservative parameter, so we can find out the overall alkalinity, but pH is not the conservative parameter, although the component, that is total carbonate and total H, are the conservative parameters. So let's first what we are going to do is that we will put this pH in the Mintek. We will keep the system open because it is mentioned that it is in equilibrium with air. So we will keep the system open. We will find out what are the components which are formed, and from that components we will calculate the alkalinity, and we will do this for the second solution also. So after the calculation of alkalinity of each solution, we can also by running these in the Mintek, we will get the concentration of all the components. So we will get the concentration of total carbonate and total H along with the alkalinity. So for the final mixed solution, we will calculate the alkalinity, and we will also find out the pH of the mixture by running the concentration of the components in the visual Mintek. So let's see how to solve this question. So let's see the question in visual Mintek. So let's go to Mintek. We have already solved it. So by go to back menu, we will reset it. So it was mentioned that the pH of the system is 9.5. So what we are going to do is we will fix the pH as 9.5. Okay. Now we have to specify the gas because it was told in the question that it is in equilibrium with the atmosphere. So we will add it. Add. It has already added. And next what we are going to do is we will run the Mintek. Okay. So this is the final distribution of the species, its concentration and activity. So we can see that these are the concentration of the different species. So we can print it to Excel, and these are the concentration of the overall components. So either we can find out the total concentration of the components of carbonate from this and H plus from this, or anyhow we have to find out the alkalinity. So we will print to Excel. So this is the result. So as we know, alkalinity is I'm writing it roughly is OH concentration of OH minus plus concentration of HCO3 minus plus 2 times concentration of CO3 2 minus concentration of H plus. Sorry, I have used the wrong syntax. So this is the alkalinity. So let's find out what will be the alkalinity. We have to calculate OH plus. So this is OH plus HCO3 minus. Okay, this is HCO3 minus plus 2 times of CO3 minus H plus. So this is H plus. So this is overall alkalinity in equivalents per liter. So we got the alkalinity of first water. Let's move to the second one. So we will again go back to Mintech. So we will edit in this also, this only. So the pH is fixed at 6.5. We have already specified the gas. Let's add it once again. So to be double sure. So give back to main menu. Now let's run the Mintech. So for pH 6.5, this is the overall distribution of the species with the concentration. So we can also print it to Excel. Let's print it to Excel. So this is the book 2. Let's find out alkalinity. It will be equal to OH minus plus HCO3 minus plus 2 into carbonate minus H plus concentration. So this is our alkalinity. Also let us find out what is the total CO3 concentration. So total CO3 concentration will be HCO3 H2CO3 plus bicarbonate plus carbonate. So this is our total carbonate concentration. Let's find out total H concentration. That will be equal to HCO3 minus, let's find out, H plus HCO3 minus plus 2 into H2CO3. Yes. And also minus of OH minus. So this will be the overall total H concentration. Let's also find out the total carbonate and total H concentration for the first water system. So let's find out total CO3, that is equal to H2CO3 aqueous plus HCO3 minus plus CO3 2 minus. So this is the total concentration in M. Next find out total H concentration, that is equal to H plus 2 into H2CO3 aqueous plus HCO3 minus concentration of OH minus. So these two are the concentration. So we have find out the alkalinity for the individual water system, for the water which was having pH 9.5 and next for the water having pH 6.5. So let us find out the total alkalinity of the mixed solution and also the concentration of carbonate and total H in the mixed solution. So let's go back to our slide. So mixing ratio here is, so let me share my second screen because it is very difficult to write in this one. So we have pH is 9.5. So for this system, we have calculated alkalinity, we have calculated total CO3 and we have calculated total H. So alkalinity was 0.030294. Total carbonate was 0.025583. Total H was 0.020873. So next we have pH at 6.5. So alkalinity is 79731 into 10 raised power minus 5. We have total carbonate as 3.11907 into 10 raised power minus 5. And we have total H as 4.444084 into 10 raised power minus 5. And we are mixing the solution in the ratio of 1:5. So let's find out what will be the alkalinity of the overall mixed solution. So this is mixed in the ratio of 1 and this is in the ratio of 5. So our alkalinity is 0.030294 volume 1 plus here the alkalinity is 1.79731 into 10 raised power minus 5, volume is 5, and overall V1 plus V2 is 5 plus 1. So our overall alkalinity will be 5.064 into 10 raised power minus 3. Now let's move to the next part. It will be equivalents per liter and total H. It is mixing ratio is 1:5. So total H is 3.516 into 10 raised power minus 3 m. Let's find out what will be the total carbonate. So the total carbonate in the first water was 0.02558 plus in the second system it was 3.1191 into 10 raised power minus 5, volume ratio 1:5, so into 1 into 5, 1 plus 5. So total carbonate is 4.3 into 10 raised power minus 3 m. So we have calculated what is the alkalinity of the mixed solution, what is the total H concentration and what is the total carbonate concentration. So again we will feed the total concentration of these two components and we will find out what is the final pH of the system. So let's go back. Let's go back to the visual mintake. Let me once see the question whether the system was open or not. So it is mentioned that there is system while mixing the system is closed. So we have to find out the pH. Let us first reset it. So we have reset it. So we have to find out the pH from mass balance. Let's add H plus. So let's see how much was H plus. It was 3.516 into 10 raised power minus 3 and carbonate was 4.3 into 10 raised power minus 3. 4.3, add to list. We will see we have added H plus and CO3 to minus, back to menu. We will run the mintake. So the final pH is 9.570 and we have already calculated the alkalinity. So let's go to the main menu. So we have already calculated the alkalinity, which is 5.064, and the final pH is, it was 9 point something, 9.56. So let's see which is the correct option. 9.56, and so A is the correct option. 5.064 into 10 raised to the power minus 3, and pH is 9.56. So let's move to the next question. So the question 4 starts from here, that in question number 3, if the system is allowed to equilibrate to the atmosphere after mixing, that is gas transfer is allowed, then what is the pH of the mixture? Provide the answer up to 2 decimal places. So in the previous question, we have calculated the pH by assuming the system is closed, because it was given in the question that there is no mass transfer of gases taking places, that is system is closed. But in the fourth question, we have to find out the pH by considering the system is open. So let's go back to the question. We have already calculated the total carbonate and total H concentration of the mixed solution. So let's go back. So we will go to the back menu. We will add the gases. It is open to the system. Sorry, it is open to the atmosphere, and partial pressure is not mentioned. So we will use the partial pressure of the atmosphere. We will add it. Yes. Now we will simply run the Mintic, because already we have added H plus and carbonate. So the pH which we are getting is 8.885, and we can see that the pH has reduced from the what was in the question number 3 when the system was closed. So we can see that there is removal of the CO2 from the mixed solution to the atmosphere. That's why, sorry, there is addition of carbon dioxide from the atmosphere to our mixed solution. That's why there is decrease in the pH and increase in the H plus concentration. So we'll go to the next question. So let's move. Sorry. So the pH was 8.88. So let's move to the next question, that is question number 5. So question number 5 starts from here, that in question 3, after the equilibrium has been reached, with the atmosphere, 1 millimolar H2SO4 is added into the solution to decrease the pH. And system is closed now. That is not in equilibrium with the atmosphere. What is the final pH? So in question number 4, we have find out the pH by considering the opening of the system. And in question number 5, we are adding H2SO4, and we have closed the system, and we have to find out what will be the final pH. So let's start solving this question. So let's go back to Mintic. And so in the question number 4, we have considered this a system to the open, and this was the concentration of all the species. These were the species present, and this was the concentration of all the species in the women tank. So now what we are going to do is we will calculate the total H and total carbonate concentration. Either we can calculate the total H by printing it to Excel, or we can directly see from here that total H is 4.693 into 10 raised to minus 3 molars. Okay, someone is, I think, joining. So either we can find out the total H and total carbonate concentration by printing this to Excel, or we can directly see from the equilibrated mass distribution, because all the species are in dissolved form. So we can also get the total concentration of the component carbonate and H plus from here. So now we are adding H2SO4 and the system is closed. So let's go back to the main menu and let's see how much H2SO4 we are adding. So since we are adding H2SO4, let's first write down what was the total H concentration by solving question 4. Total H concentration was 4 point, I think it was 4.7 millimolars, and total carbonate it was 4.89 millimolars. Now we are adding 1 millimolar of H2SO4. So as we know, each mole of H2SO4 will give us 2 moles of H and 1 mole of sulfate. So let's write down what will be the total sulfate concentration. So it will be 1 millimolar only. And total H concentration will be changed. So let me write down it from question number 4. So total H will change. It will be 4.7 plus 1. That will be 5.7. Sorry, it will be 2. 1 into 2. That will be, let me rub it. So 4.7 plus 2, because each mole of H2SO4 will give us 2 moles of hydrogen ion, so it will be 4 plus 2, 6.7 millimolars. Now we have to find out the pH of this system, which has this much of carbonate, this much of carbonate, this much of sulfate, and H total, this much of H total, and thus assuming that system is closed, we have to find out the pH. So it is similar to the previous question. We will just go back to the Mintake. Let's go back. We will reset it. Now we have to add H. It was, I think, 6.7. Let's change the units to millimolar because everything was in millimolar. So H was 6.7. We will add Just wait a second, I got a message. So H plus is 6.7. We have carbonate. Carbonate is, I think, 4.89. It was 4.89 millimolars. We will add it to the list. And sulfate was 1 millimolar. Is it? Yes, it was 1 millimolar. We will add to the list and we will simply run the Mintek because the system is closed. So the pH which we are getting is 6.554. So let's write down the final pH. 6.554. So let's go back. I got a message that there is signal problem, but today the Wi-Fi is working fine. I don't know why. So let's move to the second question. So the question is, a solution is at pH 8.35 and has reached equilibrium with the atmosphere. Okay. Now place this solution in a closed system. Then the concentration of H2SO4 that must be added to lower the pH of pH to 6 is. So we have been given a solution which is at pH 8.35 and it is open to the system and it is equilibrated with the system. Now what it is said that now we are placing this solution in a closed system and adding H2SO4 to lower the pH to 6, and we have to find out how much H2SO4 will be added. So what we will do is we will solve this question using Mintek. We will fix the pH at 8.35. We will specify the carbon dioxide gas from the gases section and we will run the Mintek. After running the Mintek, we will see the concentration of all the species present at equilibrium, and from there we will calculate the total concentration of carbonate and total concentration of H, because these two are the components which are present in the system. And again we will reset the Mintek. We will input the total H and total carbonate, and again we will go to the multi-sweep. We can go to the multi-sweep titration manager. We can specify the H2SO4 by we can do the titration of the system and specify the H plus and SO4 2 minus being added to the system. We will run the system and we will run the Mintek and we will see the iteration step in which the pH has been reduced to 6. So the pH and so the iteration step where the pH has reduced to 6, that step will give us the total H concentration. So from the H concentration which was calculated initially by considering the system closed and the H concentration which we are getting after lowering of the pH to 6, we will subtract these two values and we can divide it by 2 to get the total H2SO4 added. So there are other methods also through which we can solve. So there is a second method, is that we will fix the pH as 8.35 in the Mintek. We will specify the gas as CO2. We will find out we will run the Mintek and we will get the concentration of all the species at equilibrium. We will find out total H and total carbonate. Next, again we will go to the Mintek. We will reset everything. We will now specify the pH fixed at 6. We will specify the carbonate and H plus which we have calculated previously and we will run the Mintek. Now again a window will open in which we have been given the concentration of all the species at equilibrium. So the total H plus which we have got from the running the Mintek at 8.35, and the second one which we get from by running the Mintek at 6, we will subtract these two values and we will divide it by 2, and we will get the total sulfate which is being added. So let's see how we will solve this in Mintek. So let's go to Mintek. We will reset it first. So in the question, the pH is fixed at 8.35. Sorry. We'll specify the gas because it is open to atmosphere. We will add it. We will run them in tech. So this is the pH. This is the overall distribution of the species and its concentration. Either we can find out the total H by printing into Excel and calculating the H, or either we can get the total H and total carbonate from here. So let's print this to Excel. So this is the total carbonate and total H plus. Let's go back. Now we are fixing the pH to 6. Now we will specify the total H and total carbonate which we have calculated in the previous question. So let's see what happened. So this is the total H, that is 0.00135303. Let's copy this and let's just paste this. And also let's copy the concentration of carbonate. Let's see the equilibrated mass distribution. So we can see that the total H plus concentration has changed, and also the total carbonate has changed because we have changed the pH. So let's print this to Excel. And let's copy the previous concentration from here. Let's print out here. So earlier this was the carbonate concentration and this was the H plus concentration when pH was, I think it was 8.35. Now the pH has changed. It has changed to 6. I think I have done some mistake. Let me see. Just let me see what mistake I have done because I'm not getting the same concentration. Okay, I have not removed the CO2 gas. That's why I'm not getting the correct concentration, because in the second part it was written that we are adding H2SO4, but the system is closed now. So I have just run on the previous one. So I'm going to delete this species, and then going to run the intake. So this is the overall distribution of the components. So now I'm going to print it to Excel. Okay. Now I'll copy from the first part of the question. So this was the H plus when pH was 8.35, and this is the H plus when pH is 6, and we have added H2SO4. Let's see what is the difference between these. So it is this one minus this one. This is the overall difference, and since we know that each mole of H2SO4 will give us 2 mole of H plus and 1 mole of sulfate. So if there is difference in this much of H plus concentration, to find out how much H2SO4 we are adding, we have to divide it by 2. So this is the overall concentration. Let's increase the number of. So it is 0.0004693. Let's copy this. So this is the concentration of H2SO4 to be added. So it is near to option D. So it is equal to 4.693 into 10 raised to power minus 4 m. So option D is correct. So I'm getting a little bit higher value maybe because I have while doing the Excel calculation, the values was around 3 to 4 units after the decimal. That's why it has approximated to this value. So let's move to the next question. So this is the overall Excel which I have added. So we will first specify the CO2, and this is the fixed pH. These are the concentration. This is the total concentration of the components. Again, we have put the H plus and CO3 by fixing the pH at 6. These are the species concentration. This is the concentration of H plus and CO3 minus. And again, by doing the calculation, we will get the H plus as 4.55 into 10 raised to power minus 4 m. So this one is the last question. It is, consider a solution having pH 8 and alkalinity as 50 milligrams per liter as CaCO3. This solution is placed in a container having partial pressure of CO2 gas as 1 atm and allowed to equilibrate with the CO2 gas present. Then the pH of the solution in the container is. So we have been given the pH and alkalinity, and next so initially it is not mentioned that this is open or closed, so it is closed. and this solution is placed in a container having partial pressure of CO2 as this much, and then it is allowed to equilibrate, and then we have to find out what will be the final pH of the solution. So since we have the pH as 8 and alkalinity as 50 milligrams per liter, so we will put pH 8 and we will add the alkalinity as 50 milligrams per liter as CaCO3 in the mid-take. We will fix the pH, we will add alkalinity and we will run the mid-take. And after running the mid-take, we will see what are the various species present in the system, and we will find out the total concentration of the components, that will be H plus and CO3. And again, by getting the concentration of the H plus, total H plus, total H and total CO3, and also by adding gas CO2, partial pressure of CO2 as 1 atm. Again we will run the mintake and we will find out what is the pH of the system. So let's go to visual mintake. So let's go back. So first what we are going to do is we will reset this. So what is it is mentioned that the pH is fixed at 8 and we will specify the parameter. So from here the section parameter we can specify alkalinity. So alkalinity is specified in this problem, yes, and it is given as milligrams per liter of CaCO3. And what was the concentration? It was 50 milligrams per liter. Simply we have to do OK. It is being added and just we have to run the mintake. So we can see that these are the concentration of the various species which we got. So these are the species and these are their concentration at equilibrium. So either we can find out the total H and total CO3 by printing it to Excel and doing the calculation for total carbonate and total H, or we can directly go to the equilibrated mass distribution. And from here, we can see that total H is 1.0305 into 10 raised to minus 3. Let's print this to Excel. So this is the total H and this is the total carbonate. So let's see what is the second part of this question. Now we have to place this container in a now we are placing this solution in a container having partial pressure of CO2 as 1 atm. So in the second part of the running the mintake, what we are going to do, we will specify the total carbonate and total H that is present in the system. We will add the gas CO2 which with 1 atm as partial pressure, and again we will run the mintake and finally we will get the pH of the solution. So let's go back to main menu. Let's reset this. So we have to find out from mass balance. Okay, we will specify the H. Let's just copy this from the Excel which we have printed. H is this much. Okay, let's copy this. We will add it And again we can copy the carbonate concentration. Let's copy carbonate. Let's print this. This is a carbonate. We will add to the list. We will see if it is correct or not. Okay. The unit is molal and this much is H plus and this much is CO3 2 minus. We will go back to the menu. Now we have to specify the gases. And it was mentioned that the partial pressure is 1. So we will select from the name of the gas. It is CO2. Partial pressure is 1. We will add it to the system. Let's see. List of fixed species. Okay, CO2 is added. We will go back to the main menu and we will run the intake. So we can see that the pH has reduced to 4.815 and earlier it was 8, and by putting the system in equilibrium with CO2 with partial pressure of 1 atm, the pH has reduced to 4.815. So let's go back to our problem. So what pH we are getting? We are getting the pH as 4.815. So 4.8 is the correct option. That is B is the correct option. So the numericals which we have seen for alkalinity is that we are given a certain fixed pH or we are given alkalinity. We can simply add these in the intake to get the final total concentration of the species, that is carbonate and H. And after getting the total concentration of the components, sorry, not species, after getting the total concentration of the components, we can further follow the next step in the question. Like in this question, partial pressure of CO2 was given with which the solution were equilibrated. So we just have to put the components which we have calculated earlier. We will just specify the gas with the partial pressure and again we will run the intake and we will find the solution of the pH of the solution. So the question based, if we are doing some mixing problem, then and we know that pH is not a conservative parameter, so we cannot do mass balance on pH. We can do mass balance on conservative parameters, that is alkalinity, total concentration of the carbonate, total concentration of all the components. We know that pH is not a conservative parameter, but H total is a conservative parameter because H total shows the one of the component which is present in the system. So it is conservative, but pH is not conservative. So we cannot do mass balance on pH. So by doing the mass balance on all the components which are present in the system and also on the alkalinity, we will find out what is the concentration of the overall of all the components in the mixed solution, and also we can find out what is the alkalinity of the mixed solution. And again we will go back to the intake. We will put all the components along with their concentration and along with the condition if the system is open or if the system is closed, and then we can see if the system is open or if the system is closed, and then we can do the calculation to find, and then we can run the intake according to that, and we can find out what is the final pH or whatever is asked in the question. So let's move to the next question. So these are the screenshots from the visual intake. So the next question is in question 7. After the equilibrium of the solution with the CO2 gas present in the container has been reached, I think the question is incomplete or okay. So we have to find out which of these options are correct. So in the question 7, after equilibrium of the solution with the CO2 gas present in the container has been reached, CO2 gas is coming into the solution. CO2 gas is moving out of the solution. There is no exchange of CO2, cannot say based on the given data. So let's see. Earlier the pH pH given was 8. And the pH after putting the solution with the CO2 gas, it was, I think, 4 point something. Oh, it was 4.815. So we can see that earlier the pH was 8 and later on the pH reduced to 4.815 when the system was open to CO2 gas with partial pressure of 1 atm. So we can see there is reduction in pH. So in the week 6 lectures, in the week 6 lecture and also in the problem solving session, we have seen that when CO2 gas is when the system is equilibrated with the system, or when CO2 gas is bubbled in the system, there is no change in the alkalinity, because we know alkalinity. Okay, let me share my other screen. It's very difficult to write here. So not now. So this is the question. Earlier the pH was 8. So the earlier pH was 8, and again by again the when the solution was put with CO2 with equilibrium with CO2 with partial pressure 1 atm, the pressure pH dropped to 4.815. And in the previous last week problem solving session, and also in the lectures, we have seen that with bubbling of CO2 gas there is no change in the alkalinity, because as we know CO2 gas goes and equilibrates and form H2CO3 aqueous, and each mole of H2CO3 it gives either 1 mole of H plus and HCO3 minus, or 2 mole of HCO3 and 2 mole of H plus and CO3 2 minus. If you take the first case, 1 H plus will be added and 1 HCO3 minus 2 will be added, and it will cancel each other. And if you see the second one, then 2 mole of H plus and 2 CO3, again it will be cancelled out. 2 H plus and 1 HCO3 2 minus, it will be cancelled out. But here we are saying that pH is getting reduced from 8 to 4.815. So we can see that CO2 gas forms H2CO3 aqueous, and further it dissociates and form H plus and HCO3 minus, or it can form H plus and CO3 minus. So H plus concentration is increases, so the pH decreases. So in this system the pH is decreasing, so H plus is coming into the solution. So A is the correct option. So, and if the pH would be increasing from 8, suppose it is increasing from 8 to 10, it means that CO2 is going out of the solution, and that's why H plus concentration is decreasing, and that's why pH is increasing. But here the H plus concentration increases, so the pH decreases. So first option is the correct option. So these 8 questions were in the previous year questions for week 7. Next we will see in the I think there are 12 weeks. This is a 12-week course, and already we have finished. We are up to week 7, so there will be 5 more problem solving sessions, and again, and after that I think you have exam on 22nd, or I don't remember, it is 27th of October, and finally we will finish by, I think the last problem solving session will be on 15th of October. So after that you will have exams and this course will be over. So it is really nice to interact with you all, and these are the final questions for week 7. So thank you so much for joining. So I don't think that we have any participants. So I request you all to please join the sessions on Sunday from 3 to 5 p.m. It will help you in solving the current questions, as well as it will help you in the final examination based on all these materials for the certificate. So thank you so much. Have a nice day. Thank you.